Hello and welcome. Take a deep breath. Let the noise of the day dissolve. Let your mind drift just for a little while away from the lists and the schedules and out into the quiet. Tonight I want to talk about the greatest story ever told. It's a story you are a part of. In fact, you are its living, breathing center. It is the story of us. Not just us as people, but us as stuff. It's built around the most ancient, most human question of all. Where did we come from? When we ask this, our minds usually go to our parents, or we think of biology, of evolution, of the first single-celled life stirring in a warm, distant ocean. But tonight I want to go back further, before the oceans, before the earth, before there was even a place for life to begin. I want to ask, where did the ingredients come from? Think about your own hand. It is made of carbon and oxygen and nitrogen. The blood moving through your veins is rich with iron. Your bones are built from calcium. These aren't just ideas. They are physical things. They are elements. Tiny atoms forged in a place so violent and so magnificent it's almost impossible to imagine. Our story doesn't start in a pond. It starts in a star. Billions of years ago, long before our sun was born, there were other stars. Massive, brilliant giants burning in the dark, and for millions of years they lived by fusing simple atoms together. They took hydrogen, the simplest stuff in the universe, and crushed it into helium. And then they crushed that helium into carbon and oxygen and all the other pieces that now make up you and me and the world we're sitting on. They were the great kitchens of the cosmos. And when their lives ended, they didn't just fade away, they exploded. They scattered those precious heavy elements across space like a farmer scattering seeds. We are, in the most literal sense, the children of the stars. The carbon that makes up your DNA was born inside a dying sun. The iron that carries oxygen to your brain was forged in a supernova. So as you rest here, as you breathe, feel that connection. You are not just on the Earth. You are the Earth. And the Earth is the dust of long-dead stars. We are the universe's way of becoming aware of itself. How did that dust, that scattered starlight, find its way here? How did it learn to gather, to connect, to build, and eventually to live? That is the journey we are on tonight. Let's drift back together. Let's follow the thread. Before the 1950s, the question of how life began was a mystery that belonged more to philosophy or religion than to a laboratory. The sheer complexity of a single living cell seemed so far beyond the reach of simple non-living chemicals that its origin felt like a miracle, a divine spark that separated the living from the non-living. The origin of life was a question, but it wasn't yet a science. That all changed in '52. At the University of Chicago, a young graduate student named Stanley Miller, under the guidance of his Nobel Prize-winning professor Harold Urey, decided to stop just talking about the origin of life and try to test it. They designed an experiment that was elegant in its simplicity and profound in its ambition. They weren't just mixing chemicals, they were attempting to build a small glass model of the planet Earth as it was 4 billion years ago. Their goal was to recreate the primordial soup, a term for the cocktail of chemicals believed to exist on the young, sterile planet. Based on the best astronomical and geological data of the time, Urey hypothesized that the earlier Earth's atmosphere was not like our oxygen-rich air today. Instead, he proposed it was a reducing atmosphere, thick with gases, that had an abundance of hydrogen atoms. Miller constructed a sealed circular apparatus of glass flasks and tubes to mimic this ancient world. Into this closed system, he introduced the ingredients. He poured in water, which when heated would mimic the ancient oceans and create water vapor. Then he pumped in the gases of the primitive atmosphere, methane, ammonia, and hydrogen. This was a harsh, lifeless, and alien environment, but it was missing one crucial ingredient, an energy source. The early Earth was a violent place rocked by volcanic eruptions and critically massive constant electrical storms. To simulate the force of this lightning, Miller and Urey connected electrodes to the flask containing the gases. For an entire week, they let the experiment run, sending powerful electric sparks, tiny bolts of lightning stabbing through the chemical fog. At first, nothing happened, but after a day or two, Miller observed a fascinating change. The clear water in the bottom flask, the ocean began to turn a pale pink. As the week went on, the colour deepened, eventually becoming a dark, murky reddish-brown. The simple, clear ingredients were reacting, forming new, more complex substances. The experiment was creating gunk. When Miller and Urey analysed this brown sludge, they found something that would alter the course of science. The electricity had broken the simple molecules of methane and ammonia apart, and their atoms had recombined in new and exciting ways. The flask contained a variety of complex organic molecules. Most astonishingly, they clearly identified several types of amino acids. This discovery was a revelation. Amino acids are not just random chemicals, they are the fundamental, non-negotiable building blocks of life as we know it. They are the individual Lego bricks that biology uses to construct proteins. And proteins are the workforce of the cell. They form our muscles, act as enzymes to digest our food, and carry oxygen in our blood. To find amino acids in that flask was to find the essential stuff of life. The core meaning of the Miller-Urey experiment was earth-shattering. Complex, life-critical molecules could and would form spontaneously from simple inorganic chemistry. You didn't need a living cell to make them. You just needed simple gases and a source of raw energy. This process, the leap from non-living chemistry to the chemistry of biology, is called abiogenesis. Miller and Urey had demonstrated for the first time that the very first step of abiogenesis was not a 1 in a trillion miracle. It was a natural, predictable, and perhaps even inevitable consequence of physics and chemistry. Of course, science does not end with one experiment. In the decades that followed, the Miller-Urey experiment faced significant critiques. The primary criticism centered on their choice of atmosphere. As our understanding of planetary formation improved, many geochemists began to argue that the early Earth's atmosphere was probably not reducing rich in methane and ammonia. A more likely model suggested a neutral atmosphere, one dominated by carbon dioxide and nitrogen, the same gases we see on Mars and Venus. This was a serious challenge, and when scientists reran the experiment using this more modern carbon dioxide-rich mixture, the results were far less impressive. The yield of amino acids dropped dramatically. For a time it seemed that the iconic experiment was just a historical curiosity, a lucky guess based on the wrong assumptions. But the story didn't end there. Scientists began to offer compelling counter-arguments. While the global atmosphere may have been neutral, the early Earth was not a uniform, peaceful place. It was pockmarked with micro-environments that had very different chemistry. Consider the plumes of gas belching from an active volcano. That environment would be rich in methane, ammonia, and hydrogen, exactly the mixture Miller and Urey used. Lightning is also naturally drawn to volcanic plumes. This suggested that while life might not have started in a global soup, it could have begun in these localized, energized hotspots. Furthermore, other experiments showed that sparks weren't the only way. Scientists tested other energy sources that were abundant on the early Earth. When they blasted the gas mixtures with high-energy ultraviolet radiation simulating the intense unfiltered sunlight of a world without an ozone layer, they also produced amino acids. When they used shockwaves to simulate the impacts of comets and asteroids constantly smashing into the young planet, they also produced amino acids. It seemed the universe had many ways to cook the ingredients. Another piece of the puzzle involved the problem of concentration. A soup is by definition dilute. How could these newly formed amino acids find each other in a vast ocean to link up and form the first proteins? This is where the role of surfaces became crucial. Scientists discovered that clay, the fine mud at the bottom of a pool or on a tidal flat, has a remarkable property. Clay minerals have a structured electrically charged surface that acts like a natural magnet for organic molecules. This surface could catch the amino acids from the water, concentrating them and holding them in place. This workbench would not only bring the building blocks together, but also act as a catalyst, helping them link up into the first simple chains, the precursors to proteins. The Miller-Urey experiment, therefore, is not a final answer, but a powerful first chapter. Its true enduring legacy is that it transformed the origin of life from a philosophical mystery into a testable experimental science. It proved that the building blocks of life are not rare, precious, or miraculous. They are in fact surprisingly easy to make. The experiment showed that the universe is not a sterile, empty void that life had to fight to exist in. Instead, it suggests that the universe is primed for life. Given a few simple ingredients and a spark of energy, the laws of chemistry itself seem to have a natural tendency, an inherent bias, to move toward greater complexity, the very complexity that we call life. In the quiet of our modern world, inside every living cell, there is a perfect, intricate dance. It's a partnership between two of life's most important molecules. On one side, we have the master library, the grand blueprint. It is the molecule we call deoxyribonucleic acid, or DNA. It is a beautiful spiraling staircase, a double helix that holds the instructions for building an entire organism, the color of your eyes, the pattern of a leaf, the song of a whale. It is the legacy of life passed down through billions of years. But this magnificent library, for all its wisdom, is pendant. It is an archive. It cannot do anything on its own. It holds the story, but it cannot tell it. On the other side, we have the workers. These are the molecular machines called proteins. Proteins are the sculptors, the messengers, the builders, the defenders. They are the enzymes that digest your food, the hemoglobin that carries your oxygen, the microscopic muscles that allow you to move. They do the work, they build the structures, they make life happen. And for decades, this partnership presented us with a profound riddle, a paradox so perfect it seemed to have no solution. It is the ultimate chicken and egg problem. Think about it, to build a protein, the cell must read the instruction manual, the DNA. But the machine that reads the DNA, the machine that unzips its helix and copies its code, is itself a protein. Furthermore, the machine that builds the new protein, the ribosome, is also full of protein. So which came first? The blueprint or the builder required to read the blueprint? The information or the machine required to express that information? For life to begin, it seemed it needed this entire complex system, DNA and protein, to spring into existence all at once. It was an impossible loop. And this impossibility suggested that perhaps in the very beginning life was playing by a different set of rules. What if there was a molecule that came before both? What if in the chaotic youth of our planet there was a single remarkable molecule that could do both jobs? A molecule that could be both the architect and the builder. A single entity that could both hold the story and at the same time act to make that story real. Our search for this ancestor leads us to DNA's slightly simpler, more ancient cousin. It is a molecule that is still to this day the vital intermediary in your own cells. Its name is ribonucleic acid, or RNA. Unlike the stable two-stranded ladder of DNA, RNA is typically a single strand. This seeming simplicity is its greatest strength. While DNA is rigid like a crystal built for long-term storage, RNA is flexible. It is dynamic. Like a single ribbon, it can fold back on itself, twisting and knotting into complex, specific three-dimensional shapes. In this, RNA has a dual personality. In its sequence of letters, its bases, it can store information, a genetic message just like DNA. It can be the blueprint, but in its unique folded shape, it can act. It can become a tool. It can cradle other molecules, it can cut them apart, or it can stitch them together. It can be the worker. This was a revolutionary idea. For the longest time, science believed that only proteins with their complex structures could be the enzymes, the catalysts that speed up the reactions of life. But then in laboratories, we discovered it. We found RNA molecules that were acting as enzymes. We watched them cut and paste other RNA strands. We gave them a name that honors their dual nature, ribozymes, a blend of ribonucleic acid and enzyme. This discovery was the key that unlocked the paradox. The first life did not need the impossible partnership of DNA and protein. It just needed one molecule. It just needed RNA. The first storyteller on Earth wasn't just reading a script. It was the script, the actor, and the stage all in one. This idea is known as the RNA world hypothesis. But how can we be certain this was nearly 4 billion years ago? The evidence, it turns out, is not buried in ancient rocks. It is a molecular fossil buried deep inside you. It is hidden within the most ancient, most essential, and most universal piece of machinery in all of biology. Let's look closely at the ribosome. The ribosome is the protein-building factory. It exists in every living thing from the simplest bacterium to the cells in your brain. This machine is the one that takes the messenger RNA, the copy of the DNA's instructions, and translates it, building a chain of proteins amino acid by amino acid. For decades, we assumed this factory was like all other cellular machines made of protein. We thought the RNA inside it was just a simple scaffold holding the important protein parts in place. But when our technology finally allowed us to map the ribosome in exquisite atom-by-atom detail, we found the truth was the exact opposite. At the very heart of the ribosome, at the precise location where the new protein is being born, at the active site where the chemical bond is formed, there is no protein at all. It is all RNA. The proteins are just on the outside of the factory. They are the support beams, the external scaffolding holding the ancient RNA core in place. The work is being done by RNA. The machine that builds all the proteins is not at its functional heart a protein. It is a ribozyme. It is a living, breathing fossil. It is a direct echo from a 4 billion-year-old world, a message to us that says, I was here first. So let us drift back in time, past the dinosaurs, past the fish, past the first animals, to a time before cells even existed. Picture a warm, watery nursery on the young Earth. It is not a pond perhaps, but a porous mineral-rich vent at the bottom of the sea, or a geothermal pool bubbling with chemical energy. In this soup rich with the building blocks of life, strands of RNA are constantly forming and breaking apart. By sheer random chance, one of these strands folds into a shape that allows it to do something magical. It can grab other smaller RNA pieces and stitch them together to make a copy of itself. The first replicator is born. But the copy is not always perfect. This is the crucial, beautiful imperfection. Tiny errors, mutations creep in. Most of these errors are useless. The new RNA strand is a failure and dissolves. But every now and then, a mistake creates a better replicator. Perhaps this new strand is more stable and lasts longer. Perhaps it folds into a shape that allows it to copy faster. Or perhaps it evolves a more cunning skill, the ability to break apart other RNA strands, stealing their building blocks for its own use. This is not yet biology. This is chemical evolution. It is a molecular ecosystem. A world of competing RNA strands, all vying for resources, all replicating, all evolving. This was the RNA world, a frantic microscopic storm of creation and destruction. But this world was not the final destination. It was the bridge. RNA is a jack of all trades, but it is a master of none. As a storage molecule, it is a bit fragile and prone to errors. The double helix of DNA is far more stable, a much safer vault for the precious genetic code. And as an enzyme, RNA is good, but proteins are magnificent. Because their amino acid building blocks are more diverse, proteins can fold into a virtually infinite variety of shapes, allowing them to perform millions of complex tasks that RNA simply cannot. The RNA world, having established itself, began to experiment. A ribozyme by chance might have folded into a shape that could grab a few amino acids, the building blocks of proteins, and link them together. This first tiny, simple protein, this peptide, might have done nothing more than by chance stabilize its parent RNA like a little stone weight. But that was enough. This new partnership, this RNA strand with its tiny protein helper, was more stable. It survived better. It replicated more. This was a powerful alliance. Over vast stretches of time, this partnership grew in sophistication. The RNA storytellers began to write the code for more complex and more useful proteins. Proteins that could help the RNA copy itself even faster. Proteins that could defend the RNA from attack. Proteins that could go out and fetch new building blocks. Eventually, the system performed a grand handoff of responsibilities. The job of primary information storage, the blueprint, was transferred to the more robust and stable DNA. The job of being the primary workforce, the builders, was transferred to the more versatile and powerful proteins. And RNA, it was not discarded. It settled into the essential central role it still holds today, the vital dynamic messenger. The one who ferries the secrets from the DNA archive to the protein factory. The one who connects the past to the present. This shift from a world of pure evolving chemistry to the first glimmers of biology was not a single event. It was not a sudden flick of a switch. It was just as you imagined, like a dawn. It was a slow, subtle, imperceptible brightening. A gradual transition from the cold, dark chemistry of a barren planet to the first warm, organized systems that we would recognize as life. The chemical world gave way gently to the biological world. The system had found its elegant stable loop. The three-part harmony of DNA, RNA, and protein was in place, ready to begin the 4-billion-year journey of innovation and wonder that would eventually lead to forests and reefs, and to you sitting here breathing, thinking, and looking back, all the way to the first storyteller. And so we have this rich electric soup of potential. All the ingredients, all the building blocks are swirling in the ancient water. But there is a profound problem. They are adrift. They are lost in the chaos of the open ocean. A molecule might find a partner bond for a moment, but then the currents tear them apart. There is no focus. There is no center. For life to begin, it needs more than just the ingredients. It needs a place. It needs a boundary. It needs a way to separate inside from outside. It needs a way to say, these chemicals belong together, and that is the rest of the world. This is the first, most fundamental requirement for a self. Without a container, you don't have a life form. You just have chemistry floating in the sea. Where could this first container come from? It didn't need to be built by a complex process. It turns out the universe provides a solution that is automatic, elegant, and beautiful. The answer was found in some of the simplest molecules that were abundant on early Earth fatty acids. These are simple molecules, the basic components of what we now call lipids or fats, and they have a fascinating property. You could call it a split personality. One end of the fatty acid molecule, its head, is attracted to water. The other end, its tail, is repelled by it. Now imagine scattering billions of these tiny two-faced molecules into the water. What do? They instantly try to organize themselves. They try to hide their water-hating tails. The most stable, efficient way to do this is to team up. They form a double-layered wall, a sheet, where all the water-hating tails point inward, protected from the water, and all the water-loving heads point outward, facing the ocean. And what is the most stable shape this double-layered sheet can form? A sphere, a bubble. This is the miracle of self-assembly. No architect was needed, no instructions were read. The laws of physics and chemistry did the work themselves. These bubbles formed automatically from the fats in the primordial soup, or what we call vesicles, or more poetically, protocells. The very first cells. Suddenly, everything changed. As these bubbles formed, they captured by pure chance a tiny droplet of the surrounding chemical soup. They became the containers that life was waiting for. Each protocell was now a tiny separate reaction chamber. Inside its oily walls, the chaos of the open ocean was held back. The chemicals trapped within the amino acids, the bits of RNA, the simple sugars were no longer diluted by a planet's worth of water. They were concentrated. They were held in close confinement, forced to interact, to bump into each other millions of times every single second. The chances of complex reactions happening, of new interesting molecules being built, just skyrocketed. Each tiny bubble became its own experiment. But these bubbles were not just static, lifeless bags, they were dynamic. If a protocell floated through a patch of water rich in more fatty acids, those new molecules would join its wall and the bubble would grow. And just like a soap bubble that grows too large, it would eventually become unstable. A small disturbance, a change in water current, would cause it to stretch and pinch in the middle, and then it would divide. One large bubble would become two smaller bubbles. Here is the truly profound part. When that bubble split, what happened to the chemicals trapped inside? They were divided too. Each daughter bubble received a random scoop of the parent's internal chemistry. This was the first clumsy, beautiful whisper of inheritance. It wasn't organized. It wasn't precise like our modern DNA. It was merely a simple physical division. But for the first time, the contents of one generation were passed down to the next. This simple cycle, growing and splitting, created a brand new game on planet Earth. It was the dawn of selection. Imagine two of these protocells floating near each other. One bubble, just by luck, trapped a random mix of chemicals that did nothing useful. Perhaps they even stressed the fatty acid wall from the inside, making it weak. That bubble might burst easily, spilling its contents back into the sea. That experiment was over. But the other bubble, imagine it by pure chance trapped a molecule that helped stabilize its wall. Or perhaps it trapped a set of molecules that, working together, could actually produce more fatty acids from simpler materials. What would happen to that bubble? It would be stronger, it would be more stable, it would survive longer, and because it could build its own wall materials from the inside, it would grow faster. And if it grew faster, it would divide more often. When it divided, it would pass on those helpful molecules to its two daughter cells, and they in turn would be more stable, grow faster, and divide. This is natural selection in its most basic form. It wasn't survival of the fittest in the way we think of it, predator and prey. It was survival of the store. The bubbles that by chance had an internal chemistry that made them better at being bubbles simply continued to exist. The ones that didn't disappeared. Over millions of years, this simple selection would favor bubbles that got better and better at capturing energy, building their own parts, and copying their internal contents before they divided. This entire drama probably didn't happen in the vast empty ocean. The ideal location may have been much smaller, much more specific. Think of the pores in rocks near hydrothermal vents. Imagine a rock surface like a sponge full of microscopic pockets. Hot, mineral-rich water from the vent floods these tiny pores, bringing in fatty acids and the chemical soup. The protocells form inside these protected pockets. Then the water might recede or the area might heat up, causing the water to evaporate. This wet-dry cycle is incredibly powerful. As the water dries, all the molecules inside the protocell are forced together, becoming extremely concentrated. This is the perfect condition to force simple molecules to link up into long, complex chains like RNA. When the water floods back in, these new chains are trapped inside the bubble, ready for the next cycle. It is a humble and profound realization. The staggering complexity of life, of you, of me, of a forest, of a whale, may not have begun with a bolt of lightning. It may have begun with something as simple as a bubble. That first fragile boundary separating the self from the world was the theatre where the great story of chemistry could finally become the story of biology. While the RNA world suggests that information came first, an entirely different school of thought flips this idea on its head. This is the metabolism first hypothesis, and it argues that life is not defined by its blueprint but by its process. It argues that the engine had to be running before anyone could write the instruction manual. In this view, life is fundamentally about energy and chemistry. It is a complex, self-sustaining chemical reaction, a dynamic flow of energy that manages to keep itself going against the natural tendency toward decay. The metabolism-first hypothesis suggests that this engine of life, the continuous cycling of chemicals, the harnessing of energy, had to be established before the evolution of complex information molecules like RNA or DNA. The genetic code in this model emerged much later as a way to snapshot and stabilize this already functioning chemical system, making it more robust and repeatable. But if life is a chemical engine, where could such a system have started? Proponents of this theory look away from the calm, warm little ponds and toward the most geochemically dynamic places on Earth, the deep, dark ocean floor at the site of hydrothermal vents. This is the foundation of the iron-sulfur world theory, a powerful vision of how life could have arisen from non-living geochemistry. Forget the sunlit surface. This theory argues that life began in the crushing darkness powered not by light, but by the chemical energy of the Earth itself. At these deep-sea vents, scalding hot mineral-rich water from deep within the Earth's crust erupts into the freezing ancient ocean. This collision of extremes is what makes a perfect cradle for life. The vent water is rich in dissolved chemicals like hydrogen and sulfides. The ancient ocean water, by contrast, was cold and rich in carbon dioxide and dissolved metals like iron. The theory proposes that as this hot chemical-rich water mixed with the cold ocean water, minerals would form. Specifically, iron and sulfur would combine to create iron sulfide, also known as pyrite or fool's gold. These newly formed mineral surfaces were not just simple rocks, they were the first catalysts. A catalyst is a substance that speeds up a chemical reaction without being used up by it. The iron-sulfur world theory suggests that the surfaces of these iron sulfide minerals acted as the first primitive enzymes. They provided a structured environment, a workbench where simple molecules could gather. Imagine the ocean's carbon dioxide molecules sticking to the surface of this pyrite. At the same time, the hydrogen-rich vent water flows past. The mineral surface holds the carbon dioxide in place, allowing the energy from the hydrogen to attack it, forcing these simple molecules to react and link together. This process, powered by the natural chemical energy of the vent, could have started building longer and more complex organic molecules from the simplest of ingredients. This system harnesses a powerful gradient. A gradient is simply a difference, and differences are a source of energy. Think of a waterfall. The water at the top has high potential energy which is released as it falls. The hydrothermal vent is an energy gradient. There is a massive chemical difference between the hydrogen-rich fluid coming out of the vent and the carbon dioxide-rich water around it. This imbalance is like a natural battery. Life in this view did not have to invent a power source. It simply tapped into one that geology had already provided. A more recent and compelling refinement of this idea focuses on a specific type of vent alkaline hydrothermal vents, like the Lost City field in the mid-Atlantic. Unlike the fiercely hot and acidic black smokers, these vents are cooler, longer-lived, and crucially alkaline basic. The rock structure of these alkaline vents is porous, like a sponge filled with countless microscopic interconnected mineral-walled pockets. These tiny pockets are perhaps the most exciting part of the theory. They function as natural protocells. Think about it, a cell is just a container that separates the inside chemistry from the outside world. These tiny mineral pores in the vent rock do exactly that. They provide a confined space where chemicals can concentrate and react without floating away into the open ocean. But they provide something even more profound. The vent fluid inside the pores is alkaline and rich in hydrogen. The ocean water outside the pores is acidic, or at least less alkaline and rich in carbon dioxide. This creates a natural proton gradient across the thin mineral walls of the pore. This is staggering because a proton gradient, a difference in the concentration of protons, is exactly the same power source that all living cells on Earth use today. Your own cells right now are using this exact mechanism to generate their energy currency. These alkaline vents built by geology alone naturally create the precise energy-generating conditions that are universal to all life. Even more striking are the similarities to our own modern metabolism. The Krebs cycle, or tricarboxylic acid cycle, is the central engine of energy production in our cells. It is the core process that takes the food we eat and converts it into the energy that keeps us alive. When scientists simulated the conditions of an iron-sulfur world in the lab, with the right minerals, temperatures, and simple chemicals, they found that the reactions that occur spontaneously are very similar to a reverse or primitive version of the modern Krebs cycle. This suggests that our own metabolism is not some brilliant invention of complex evolution. Instead, it may be a chemical fossil. It's the echo of reactions that were already happening, driven by geology on the ocean floor 4 billion years ago. Life didn't invent this chemistry. It was born from it, adopted it, and then spent the next 4 billion years perfecting it. In this metabolism-first model, life was not a singular miraculous event. There was no spark. Instead, there was a slow, gradual transition. It began as simple geochemistry, minerals, water, and energy gradients. This geochemistry became increasingly complex, organizing itself into self-sustaining loops and cycles within the protective mineral pores of the vents. This proto-metabolism ran for thousands, perhaps millions of years, growing more stable and efficient. Only much, much later, as this engine was running at full steam, did the first information molecules like RNA begin to form, learning to record and replicate the successful chemical pathways. The blueprint in this world was the last piece of the puzzle created to copy the engine that was already a proven success. As we rest here suspended in the quiet darkness, our minds have been drifting through the great expanse. We've journeyed through the impossibly large and the impossibly small. We have been searching our own planet, digging deep into its ancient rocks and peering into the boiling vents of its deepest oceans. We are searching for a single moment, the moment that a collection of simple lifeless chemicals crossed a magic threshold and became alive. We've been searching our home for the answer. But what if the answer isn't here? What if the story of life on Earth doesn't begin on Earth? This is the heart of a beautiful and compelling idea, a hypothesis known as panspermia. The name comes from ancient Greek and it simply means seeds everywhere. It's the theory that life, or at the very least the essential complex building blocks of life, are not a local phenomenon. That they are in fact common throughout the universe, drifting through the vast emptiness of space like cosmic pollen on a galactic wind. This idea suggests that our planet was not a sterile laboratory where the recipe of life was invented from scratch. What if instead it was simply a warm, safe and fertile garden waiting for a seed to be delivered? What if that spark, that flicker of animation that now resides in you, in your very DNA, is part of a story that is billions of years older than the Earth itself? What if we are in the most literal sense the children of the cosmos? It's a lovely thought, but is there any reason to believe it? Or is it just poetry? Well, let's look up. When we stare into the night sky, the space between the stars looks perfectly empty. A cold, sterile black vacuum. But when we point our most powerful telescopes at that darkness telescopes that can see in wavelengths of light and energy far beyond our limited human sight, a new picture emerges. That emptiness is not empty at all. It is filled with enormous swirling majestic clouds of gas and dust. They are unimaginably vast, trillions of miles across. We call them interstellar clouds. They are the great cosmic factories. They are the nurseries where new stars and new planets will one day be born from the collapse of this very dust. For decades we assumed these clouds contained only the simplest atoms, hydrogen, perhaps some helium. But as our instruments grew more and more sensitive, we started finding surprises. We found water. We found oceans of water frozen into tiny grains of dust. Then we found familiar chemicals like methane and ammonia, and then we started finding things that sounded like they belonged in a biology textbook. Floating in these cold, dark, ancient clouds the universe is already building. We have found formaldehyde. We have found different types of alcohol. We have even found simple sugars. These are not just random atoms, these are complex organic molecules. That word organic simply means that the molecule is built around a backbone of carbon, the very same element that forms the backbone of every single living thing on Earth. Let that sink in. In a cold cloud of gas floating in the dark billions of years before a planet even forms, the universe is already busy building the essential ingredients for life. It's not even waiting for a warm, comfortable world. The cosmos, it seems, is chemically biased toward complexity. It wants to build these shapes. These clouds are like the galaxy's spice cabinet full of the pre-mixed foundational ingredients needed for the recipe of biology. They are floating there, waiting for gravity to pull them together to ignite a new star and to form a spinning disk of dust and rock, a disk that will eventually become new planets. Planets that will be born from their very first moment already seasoned with the very molecules that on our world eventually led to us. But those clouds are so very far away. How could those ingredients get from that distant cloud to us? The answer, it seems, falls right out of the sky. Our solar system is a wonderfully messy place. It is filled with the leftover debris from its formation 4.5 billion years ago. It's cluttered with asteroids and comets, and sometimes pieces of these ancient wandering bodies end their long journey by striking our planet. When they survive the fall, we call them meteorites. They are messages from the distant past. They are rocks that have been drifting unaltered in the cold vacuum of space since before the Earth itself was even fully formed. They are pristine time capsule samples of what our solar system was originally made of. And in the sun, in a small town in Australia called Murchison, a very special message arrived. A large meteorite broke apart in the atmosphere, scattering dark carbon-rich fragments across the land. Scientists gathered them quickly before they could be contaminated by earthly soil or rain. And when they carefully analysed what was inside, they found something that changed our understanding of the universe. They didn't find aliens, they found something in a way far more profound. They found amino acids. Amino acids are the links in the chain. They are the molecular building blocks that all life on Earth uses to build proteins. And proteins are the little machines that do all the work inside your cells. Your body is built from them. And here they were, inside a rock that came from deep space. And these weren't just one or two simple kinds. They found over 70 different types of amino acids. Many of them are not even used by life on Earth. This was the first definitive proof. The stuff of life wasn't just being made in distant theoretical clouds, it was right here in our own solar system and had been from the very beginning. But the story doesn't end there. As our scientific tools became even more precise, we looked again at the Murchison meteorite and at others like it. We found sugars, and we found things called nucleobases. These are the letters of the genetic code. The A, T, C, and G that make up our DNA. The very instruction manual for life, your instruction manual, was found fully formed inside a piece of space rock. The early Earth 4 billion years ago was not a quiet, sterile pond. It was a chaotic, violent place. It was being continuously seeded from above. It was a cosmic delivery system, a bombardment of comets and asteroids bringing water to fill our oceans and bringing the very blueprints of biology. So the ingredients are out there, and they can be delivered. That alone is a staggering, beautiful thought. But the panspermia hypothesis has an even bolder, more radical version. What if it wasn't just the ingredients that arrived? What if life itself, tiny, simple microbial life, made the journey through space? At first, this idea sounds like pure science fiction. Space is the most hostile environment we can possibly imagine. There is the crushing absolute cold. There is the hard vacuum which would boil away all unprotected water instantly. And most of all, there is the relentless sterilizing bath of ultraviolet and cosmic radiation pouring from our sun and from distant exploding stars. Surely no living thing could survive that. But life is far more stubborn, more resilient than we ever thought possible. Here on Earth, we have found it in places we thought were sterile. We have found it in the boiling acidic water of geothermal hot springs. We have found it in the super salty freezing brine hidden deep under the Antarctic ice. We have found it miles beneath our feet, deep inside solid rock, living on nothing but chemical scraps and existing on a timescale of thousands of years. We call these organisms extremophiles. They are the lovers of extreme conditions. So we decided to test them. In a series of experiments, we took some of these incredibly hardy bacteria and we put them on a panel on the outside of the International Space Station. Not inside where the astronauts are safe and comfortable, but outside, exposed to the raw vacuum, exposed to the brutal, unfiltered radiation of space. They were left there for years. When the astronauts retrieved the panel and brought it back to Earth, we found something that defied belief. Many of them had survived. They had used the bodies of their dead companions on the outer layer to form a tiny protective crust, a shield against the radiation. And the ones on the inside, they had simply gone dormant. They had waited. This tells us that survival in the vacuum of space, at least for a time, is possible. Now picture this. Imagine a large asteroid striking a planet that already has life, perhaps a young Mars which we now believe was once wet and warm with rivers and lakes. That impact would be catastrophic. It would blast billions of tons of rock from the Martian surface, throwing it into space with such violence that it would escape the planet's gravity. Some of those rocks would be large enough to shield any microbes hiding deep inside them from the heat of the impact and the radiation of space. Those rocks, now newborn meteorites, would begin their own long journey, drifting through the solar system for thousands or even millions of years. And eventually some of them would cross the orbit of another planet, a planet like an Earth. It is a statistical certainty that we have pieces of Mars on our world right now delivered by this very process, and it is entirely possible that inside one of those ancient rocky travelers life hitched a ride. Now we must pause for a moment of quiet scientific honesty. This beautiful idea, panspermia, even if it is proven to be true, it doesn't actually answer the ultimate question. It doesn't tell us how that first spark of life happened. It doesn't explain how a random collection of non-living chemicals, those amino acids, those sugars, crossed that mysterious sacred threshold and became the first living replicating cell. All it does is move the location. If life didn't start on Earth but started on Mars, we are still left with the exact same question: how did life start on Mars? If it came from a cloud in another star system, how did it start there? Panspermia doesn't solve the problem of abiogenesis, the origin of life from non-life. It only suggests that the origin event itself might be incredibly rare, perhaps only happening once or a few times in an entire galaxy. And then it spreads. It suggests that starting life is hard, but spreading it is easy. But what this idea does give us, and what is so deeply comforting as we rest here, is a sense of connection. It takes our biology, which feels so small, so fragile, and so specific to this one blue world, and it frames it as a cosmic phenomenon. It suggests that we are not a bizarre accident, a 1 in a trillion fluke confined to a single lonely planet. Instead, it suggests that life is a fundamental property of the universe, just like gravity or light or the formation of stars. It paints a picture of a cosmos that is fertile, a universe that is alive, constantly building the blocks, seeding its planets and sharing the potential for consciousness. When you look at your own hand resting in the darkness, you are not just seeing Earth stuff. You are seeing the processed, recycled dust of ancient long-dead stars. You are seeing the amino acids that were forged in the cold vacuum of space. You are seeing a biological lineage, an unbroken chain of life that may be billions of years older than the sun itself. You are not separate from the cosmos. You are a part of it. You are the cosmos. Finally, after all this time observing and wondering and dreaming of its own origin, we have journeyed together from the quiet birth of the first atoms to the churning chemical-rich cauldrons of a young planet. We have seen the universe patiently assemble the bricks and mortar of biology, the amino acids, the lipids, the sugars. We have the ingredients, but a pile of bricks, no matter how perfect, is not a home. A collection of chemicals, no matter how complex, is not life. It is just a pantry waiting for a chef. The great leap, the threshold we now approach, is the moment those ingredients stop being isolated passive molecules and begin to act upon one another. It is the moment they organize. This is the transition from mere chemistry to the grand cooperative dance of integrated chemical networks. The engine that drives this new dynamic order has a beautiful name, autocatalysis. It sounds technical, but the concept is beautifully simple. Imagine a chemical reaction, a very common one. Molecule A meets molecule B, and they combine to create a new molecule C. In normal everyday chemistry, this might happen slowly just by chance, but in an autocatalytic set, molecule C has a special talent. Its very presence in the water acts as a helper, a catalyst that encourages A and B to meet and combine much faster. The result is a powerful feedback loop. The more C you have, the faster you make C. It is a reaction that pulls itself up by its own bootstraps. It is a tiny chemical seed of self-perpetuation. It is the first whisper of growth, of replication. Now imagine this not as a single loop, but as a vast interconnected web. Imagine molecule C doesn't just help make more C, but it also helps to create molecule D. And molecule D in turn helps to create E, which then perhaps several steps later helps to create the original A or B again. This is a network, a chemical family where every member helps the others. This is where the story becomes truly profound. In that primordial ocean, there wasn't just one of these experimental networks. There were millions, all forming by chance and all competing for the same raw materials. They were all competing for the available A's and B's in the environment. Many of these networks were fragile. They were inefficient, slow, or their products were unstable and quickly fell apart. They were chemical dead ends. But other networks, just by chance, were more stable. They were faster. They were more efficient. These robust networks didn't just survive, they thrived. They greedily consumed the raw materials from the environment and grew, reinforcing their own cycle, making it stronger and faster. This is a form of natural selection, but it is happening at a purely chemical level. The environment itself, the temperature, the acidity, the available materials is relentlessly testing these systems. The networks that are more stable, the ones that are more efficient at grabbing energy and materials, are the ones that persist. Scientists call these stable, self-sustaining states chemical attractors. The name is perfect. Imagine a vast landscape with many hills and deep valleys. If you drop a marble anywhere on this landscape, it will roll downhill pulled by gravity and eventually come to rest in the deepest, most stable valley. That valley is an attractor. In the same way the chaotic random mix of chemicals in the early ocean would roll and settle into these highly stable, self-sustaining network patterns, the system was finding order in the chaos. But this raises a crucial cosmic question. There is a fundamental law of the universe, the second law of thermodynamics, that tells us everything must move toward disorder. Everything tends to break down. A hot cup of tea always cools. A built structure eventually crumbles. This state of balance, this equilibrium, is the natural endpoint for all things. But for chemistry, equilibrium is a dead end. A network in perfect balance does no work. It is static. It is by all definitions dead. So how did these fledgling networks avoid this fate? How did they defy the universe's greatest law? They cheated. They were not closed systems. They did not exist in a sealed box. They were open systems existing in an environment with a constant, relentless flow of energy. Think of a whirlpool in a river. A whirlpool is a magnificent, highly ordered structure. It is not in equilibrium. It is a place of intense activity. It can persist for days, even years. Why it persists? Because the river is flowing. The constant stream of water and energy moving through the whirlpool is what sustains its complex pattern. If the river dries up and becomes a still pond, the whirlpool vanishes instantly. These early chemical networks were not a pond, they were a whirlpool. They were constantly taking in high-energy food, perhaps simple molecules rich in chemical potential from deep-sea vents or compounds energized by the young sun's ultraviolet light, and they were constantly releasing low-energy waste. This continuous flow of energy, this constant throughput, is what kept the network alive. It is what held back the tide of disorder. This right here is the very first flicker of metabolism. It is the art of existing in a state of permanent imbalance. Life is not a static object. It is a process. It is a stable pattern, a flame sustained by a constant flow of fuel. And this leads to one final beautiful idea. When we think of life, we think of information. We think of DNA, the blueprint, the master instruction manual. But where was the manual for this? Here is the secret. The information was the network. The blueprint was the house. Think about it. The information on how to make the autocatalytic cycle work was not written down on a separate molecule. It was stored in the physical structure of the cycle itself. The presence of molecule C was the instruction, make more C. The system remembered how to survive simply by being the system that survived. The pattern of the whirlpool is itself the information for the whirlpool. Information in its most basic form is just a reduction of uncertainty, a stable pattern where there could be chaos. A stable chemical network is a profound island of order. This structural information, this self-perpetuating pattern, existed long before a single strand of RNA or DNA ever formed. The software and the hardware were for this brief magical moment exactly the same thing. This then is how order begins to emerge. It is not a single miraculous event. It is a gradual, logical and breathtaking convergence. It is the moment when chemistry driven by the laws of physics begins to fold in on itself. Life we see does not arise in spite of the universe. It arises because of it. It is the profound result of a conversation between chance and feedback. Chance provides the endless experiments, the random bumping of molecules. Physics and chemistry provide the feedback, the rules of the game, relentlessly deciding which experiments will last and which will fade back into the soup. As we drift here in this quiet ocean of stars, our thoughts turn from the general to the specific. We have spoken of the vastness of the cosmos, the emptiness that defines it. We have spoken of the impossible luck of this planet and the unique life-giving solvent we call water. But now we must talk about the architect. We must talk about the element that takes the chaos of the universe and organizes it into life. It is the single atom upon which our entire existence is built, an element so common, so fundamental that we write with it, we burn it for fuel, and we are composed of it. Let us spend these next few moments in quiet contemplation of the miracle of carbon. Why carbon? Why this one atom? Out of all the 118 known elements in the Great Periodic Table, why did life choose this one? The answer is not a complex mystery. It is a simple, elegant piece of chemistry. It is a matter of geometry. An atom of carbon arrives at the cosmic dance with 4 hands to hold. In the language of chemistry, this is called 4 valence electrons. It's the perfect number. It's not so few that it gives its electrons away easily like sodium. It's not so many that it aggressively rips them from others like fluorine. Carbon is made to share. It forms 4 perfect stable partnerships. It creates what we call covalent bonds. And this number 4 is the key to everything. This isn't just a number, it is a license for infinite creativity. Think of it as the ultimate architectural building block. A block with only one connector is just a cap. A block with 2 connectors can only make a simple chain a straight line. But a block with 4 connectors, 4 points of attachment, can build in 3 dimensions. It can build up, down, left and right. This is carbon's unrivaled flexibility. With these 4 bonds, carbon can link to other carbon atoms one after another, creating long stable chains. These are the foundations of the fats, the lipids that create the very membranes of your cells, the delicate, intelligent walls that separate you from the universe. But carbon doesn't just build straight lines. It can branch out like the intricate branches of a tree, creating complex molecules that store energy like the glycogen in your muscles. And most beautifully of all, it can loop back on itself. It can form rings, stable, elegant rings of 5 or 6 atoms. These rings are the fundamental shape of the sugars like glucose, the very fuel that is powering your brain as you listen to my voice. These rings are the basis of the nucleotides, the letters of your DNA. Carbon builds chains, it builds branches, and it builds rings. It is the only element that can do this with such stability and such variety. It creates a molecular landscape of staggering complexity. And it does so with a perfect balance. The bonds carbon forms are strong, they are stable, they don't just fall apart if the temperature changes slightly. They can hold the structure of a complex protein together for years. But they are not too strong. They are not permanent. They can be broken when needed with a gentle push of energy. This is the flexibility of life. Life must be stable, but it must also be dynamic. Carbon provides both. You might wonder, is there an alternative? Science fiction writers love to imagine life based on another element. The most popular candidate is silicon. If you look at the periodic table, silicon sits right beneath carbon. It too has 4 hands to hold. It too can form 4 bonds. So why aren't we silicon-based? Why don't we see silicon trees and silicon animals walking this planet? On a dry, very hot world, perhaps it could be possible. But here on our Earth, dominated by water, silicon simply cannot compete. The problem is that silicon atoms are larger. Their connections are clumsier. The bonds they form, especially with themselves, are weaker. A silicon-silicon chain is brittle. It shatters. A carbon-carbon chain is flexible. It bends, it folds, it twists. Think of it this way, silicon structures are like glass. Carbon structures are like plastic or wood or fibre. One is rigid, the other is adaptable. But the most important difference, the one that makes carbon the undisputed champion of life, is its relationship with oxygen. Life as we know it is a process of energy. It needs to take in fuel and release waste. This is metabolism. When carbon combines with oxygen, it creates carbon dioxide, a gas. When you exhale, you're releasing carbon dioxide. It's a small light molecule. It floats away effortlessly, it dissolves in the water of the oceans. It can be taken up by a plant. The cycle continues. The system flows. Now imagine if we were made of silicon. When silicon combines with oxygen, it creates silicon dioxide. We have a common name for this molecule. We call it sand, or quartz. It is a rock. Imagine trying to live, trying to run a metabolism. If every time you exhaled, you released a tiny grain of sand, the system would lock up. It would grind to a halt. Life needs to flow. Carbon flows. Silicon on a wet, oxygen-rich world like ours just stops. And so carbon is the backbone. It is the skeleton of every living molecule. Think of the proteins that make up your muscles, your hair, your skin, the little biological machines that do all the work in your cells. They are nothing but fantastically long, folded and twisted chains of carbon atoms decorated with nitrogen, oxygen and hydrogen. Think of your DNA, that famous beautiful double helix, the blueprint for all of you. What is the spine of that spiral staircase? It is a long repeating chain built from a 5-carbon ring, a sugar. Think of the lipids, the fats that form the soft boundary of every one of your trillions of cells. They are long straight tails of carbon atoms. Carbon is the framework, it is the scaffolding, it is the architecture of all life. But its role is even deeper than that. Carbon is not just the material of life, it is also the currency of its energy. This is the part that connects us all from the smallest bacterium to the largest whale. Think of a single photon of light, a tiny packet of energy from the sun travelling 93 million miles to strike a leaf. That leaf, in the quiet miracle of photosynthesis, takes atoms of carbon dioxide from the air. It uses that captured sunlight to snap those carbon atoms together, forcing them into bonds with each other to build a molecule of sugar. The sun's energy is now trapped. It is no longer light, it has become chemical energy stored in the bond between those carbon atoms. That leaf, that plant is the battery of the world. Then an animal eats the plant, or we eat the plant, or we eat the animal that ate the plant. And in our own cells, in the tiny powerhouses called mitochondria, we perform the process in reverse. We call it respiration. We breathe in oxygen, and our cells with incredible precision gently step by step break those carbon-carbon bonds. And as each bond breaks, that ancient sunlight trapped in a leaf, perhaps days or months ago, is released. That release is the energy that is powering your heart to beat. It is the energy that is allowing your brain to process these words. It is the warmth of your body. The flow of energy in all of the Earth's biosphere is nothing more than the making and breaking of carbon bonds. Carbon is the great broker of solar energy. And now we come to the final, most profound and most contemplative part of our journey with this element. Where did it come from? If we go back to the very beginning, back to the Big Bang, the universe ignited in a flash of unimaginable energy. In those first few minutes, it created the first elements. It created hydrogen in vast, vast quantities. It created some helium and a tiny, tiny trace of lithium. And that's it. The Big Bang did not create carbon. The early universe was almost entirely hydrogen and helium. There was no carbon. There was no oxygen. There was no iron. The elements of life did not exist. So where did they come from? They were forged. For millions of years, those first clouds of hydrogen and helium drifted. They swirled. Gravity pulled them together into massive, dense knots. The pressure at the center of these knots became so immense, the temperature so high that a new fire was lit. The first stars were born. These stars spent their lives fusing hydrogen into helium, but for life that is not enough. It was only when these first massive stars began to die that the miracle happened. In the collapsing, superheated core of a dying star, the pressure became even greater. The star in its final throes began to fuse helium. In a process of incredible violence and perfect precision, 3 nuclei of helium was slammed together. 3 atoms of helium become 1 atom of carbon. An atom with 6 protons and 6 neutrons. A new stable, versatile element was born into the cosmos. That star at the end of its life exploded. It became a supernova. It shattered itself, scattering this newly minted carbon, this precious star stuff across the dark voids of the galaxy. Like a farmer sowing a field, this carbon, this ash of a long-dead star drifted. It mixed with other clouds of gas and dust. It cooled, and eventually, generations later, it became part of a new cloud, a new nebula. That nebula collapsed. It formed our sun, it formed our solar system, it formed the planet Earth, and it formed you. The carbon in your bones, the carbon in your DNA, the carbon in your breath. Every single atom was forged in the heart of a star that lived and died billions of years ago. When you look up at the night sky, you're not just looking out, you're looking back at your own origins. We are in the most literal sense stardust. And this changes our perspective on life, doesn't it? Life is not some strange, improbable miracle that defied the laws of the universe. Life is the universe. It is the natural, perhaps inevitable result of carbon simply following its own rules. It is the result of carbon's ability to build, to connect, to form complex, stable and flexible structures. Life is the result of carbon's ability to capture the energy of a star and pass it along from a plant to an animal to a thought. Life is the universe through the chemistry of carbon finding a way to organize itself to become complex and in us to wake up. We are the cosmos made conscious. We are the atoms from those ancient stars now gathered together for a short time, able to wonder, to feel and to contemplate the very stars from which we came. Let that thought settle. Feel the connection. The ground beneath you, the air you breathe, and the fire of the stars. It is all one system. You are not separate from it. You are a part of it. A living, breathing, thinking part of the cosmos. All thanks to the simple, elegant, four-handed atom. The atom of all life. But there was a problem. A profound one. Even if we have this magical ocean, this primordial soup filled with all the right ingredients, amino acids, sugars, and perhaps even those clever strands of ribonucleic acid, how does anything happen? The ocean is vast. It is the definition of dilution. Imagine trying to build a complex machine, but your tools and parts are scattered randomly across an entire continent. The chances of the right parts finding each other in the right order are almost zero. The ancient ocean was the same. A molecule of ribonucleic acid capable of copying itself might float for 1,000 years before it ever found the building blocks it needed to make that copy. The chemistry of life is complex. It needs to be focused. It needs a container. We think of life as a cell. and we think of a cell as a bag, a membrane made of lipids or fats that holds all the important machinery inside. But creating that perfect fatty membrane is itself an incredibly complex biochemical process. It seems unlikely that such a perfect container would be the first step. So how did life solve this concentration problem before it had invented the modern cell wall? This is where a remarkable idea proposed decades ago by the Soviet scientist Alexander Oprin floats gently back into view. He looked at the simple raw ingredients of that early soup, not just the small molecules but the long chains they formed. Long sticky chains of proteins and long sugary chains of polysaccharides. He suggested that life's first container wasn't a wall at all, it was a droplet. He called them cocovates. It sounds like a complicated word, but it describes a physical process you have seen 1,000 times. Have you ever made a salad dressing? You take oil and vinegar, you put them in a jar and you shake. For a moment it's all mixed together, cloudy and chaotic. But then you let it rest, and slowly the oil begins to find itself. It separates from the water-based vinegar. The oil molecules cluster together, forming distinct oily bubbles suspended in the vinegar. This is called liquid-liquid phase separation. It's not a chemical reaction, it's just physics. Two liquids that don't want to mix separating themselves into distinct phases. Oprin realized that the primordial soup would do the same thing. It wasn't just water, it was water filled with these long, complex, sticky polymers. And under the right conditions, the right temperature, the right saltiness, the right acidity, these polymers would suddenly decide they preferred each other's company more than the water's. They would separate. They would pull themselves out of the general solution and cluster together into tiny, microscopic, gummy droplets. They weren't bubbles of air. They were rich, concentrated bubbles of stuff floating in the thinner, watery soup around them. And right here in this simple physical act, something profound happens. For the first time, there is an inside and an outside. This is the very first faint whisper of identity. This droplet has a boundary. It's not a strong, permanent wall, just a fuzzy physical border, but it's a border nonetheless. It separates a tiny patch of the universe from all the rest of the universe. But the real magic is what happens next. These cosivate droplets are not passive, they are dynamic. Because of their chemical nature, they interact with the soup around them. They pull things in. Imagine our lonely molecule of ribonucleic acid floating in the vast ocean. It drifts near one of these droplets. The droplet's surface chemistry might be attractive to it and pull, it gets drawn inside. The same happens for the building blocks, the sugars, the phosphates. Suddenly the concentration problem is solved. Outside the droplet, the ocean is dilute and lifeless. But inside the droplet, the ingredients for life are now gathered in a dense, crowded chemical stew. Reactions that would take 1,000,000 years in the open ocean can now happen in seconds. The droplet becomes a tiny chemical factory. It becomes an engine. It focuses the power of the soup. And these droplets don't just sit there. They behave in ways that seem uncannily alive. As they absorb more and more polymers and chemicals from the water, they get bigger. They grow. And as they grow, they become less stable. A simple disturbance, a small wave, a current, even just their own internal physics can cause a large, unstable droplet to split. It divides into 2 or 3 or 5 smaller droplets. This is not biological reproduction, not yet, it's just physics. An oily bubble getting too big and breaking apart. But think about what it means. You now have a system that can grow and divide. You can even imagine a simple form of competition. Picture 2 droplets side by side. One droplet, by the sheer chance, has a chemical makeup that is slightly better at pulling in raw materials from the soup. It grows faster. It divides more often. The other droplet, which is less efficient, can't compete for the same resources and might even dissolve back into the soup. This isn't Darwinian evolution. There is no information, no genetics being passed down. It is purely physical selection. The most stable, efficient droplets persist. This is the messy, chaotic, beautiful beginning. This is life before life. And now we can bridge the 2 ideas. What happens if one of these coservate droplets, this busy little factory, this body, happens to trap one of those special molecules of ribonucleic acid inside it? Now you have the ultimate partnership. You have the instructions, the ribonucleic acid living inside a container, the cocovate. The container does the hard work. It provides a safe home. It goes out and gathers the food, the raw chemical building blocks, and concentrates them. It feeds the instructions. And the instructions, safe and well fed, can now get to work. They can start to copy themselves. Maybe they even learn to build a simple protein that makes the droplet itself more stable. This is a protocell. It is a hybrid system. A temporary messy body of concentrated chemicals home to a tiny piece of information. It is a profound step because it shows us that life didn't need to begin with a miracle. It could have begun with simple physics, the same physics that separates oil and water. Life, it seems, didn't begin with a perfect finished blueprint. It began as a messy, fleeting, accidental bubble, a temporary safe place formed from the soup itself where the first faint sparks of chemistry could finally gather focus and ignite. And so our long journey through the cosmic orchestra brings us to this quiet final movement. We have travelled an immense distance, not just across the dark gulfs of space, but through the very essence of what it means to be alive. We have followed a story that began in the unimaginable fire of the beginning, and we are now in this very moment living inside its latest, most intricate chapter. Let's rest here for a moment and look back at the path we have walked together. We began with the spark. We witnessed it in the hearts of colossal dying stars. These were the great cosmic forges that in their final fiery moments crushed simple elements like hydrogen and helium into the heavier atoms that make everything else possible. They created the carbon, the oxygen, the iron. This was the first act, the violent, generous birth of the ingredients. From that cloud of stardust, we watched the molecules form. In the cold, quiet darkness between the stars, these new atoms began to link together. We saw carbon, the great builder, the most sociable of elements, begin to form the long, complex chains that would one day become the backbone of life. It was here in these dark nurseries that the first whispers of chemistry began. Then we followed the drop. We tracked the journey of water frozen onto dust grains and locked inside comets. We saw it travel across the new solar system to seed a young rocky Earth. This water gathered into the first oceans a vast, gentle and stable cradle. It became the ultimate solvent, the stage where the molecules could meet, mingle and begin their slow, patient dance. And finally we observed the cycle. We saw that life is not a static thing, but a constant flowing process. We saw the great carbon cycle where atoms move from the air to the oceans into living things and back into the earth, a breath that spans millennia. We saw the water cycle rising as vapor falling as rain, a pulse that keeps the planet alive. As we look back at this incredible cascade of events, a profound truth becomes clear. Life was not a single instantaneous miracle. It was not one lucky strike in the darkness. Instead, life is a convergence. It is the meeting point of countless different pathways, each one necessary, each one unfolding over billions of years. It required the right kind of star burning with the right steady light. It required the right distance from that star, a perfect zone where water could be a liquid. It required the right ingredients forged in stars that lived and died long before our sun was even born. It required the right shield, a magnetic field to protect the fragile emerging chemistry from cosmic radiation. All of these separate streams, physics, geology and chemistry, flowed through time, and right here on this small blue world they met. If we think of this grand story as a beautiful complex piece of music, then carbon has written the language. It provides the structure, the grammar, the rules that allow for complex information to be built and stored. But it is chemistry that sings the melody. Chemistry is the force that gives the language its voice. It is the energy in the spark, the subtle attraction between the molecules, the life-giving flow of the drop, and the steady repeating rhythm of the cycle. It is the grand unfolding song of the universe. And you are not separate from this song, you are an expression of it. The atoms that make up your body right now are the same atoms that were forged in those stellar fires. The water within you has cycled through ancient oceans and endless rain. The very same chemical laws that shape the nebulae and ignite the stars are the laws that are quietly at work within you in this moment. You are the universe reflecting upon itself. You are the chemistry that learned to wonder. As you close your eyes and prepare for rest, feel that connection. Feel the gentle, steady rhythm of the cosmos. The pulse of the cycles, the memory of the stars, the quiet hum of the chemistry within. You are a part of it all. You are home. Rest now in the peace of that melody. Good night.